Hi, my name is Xia. I'm here to present a legged soft robot platform for dynamic locomotion. This work was done in collaboration with Jiaming Fu, Hongbo Zhu, Zhicheng Song, Yibo Jiang, and my advisor, Professor Hod Lipson. Research on dynamic locomotion for legged robots has been primarily focused on rigid mechanisms. While rigid robots can be programmed with active compliance to adapt to the environment, soft robots can take advantage of their deformable structure to achieve passive compliance, which makes them potentially more adaptable than rigid robots. Unfortunately, research on dynamic locomotion for soft robots is limited, and only a handful of soft robots are capable of fast locomotion with a speed greater than 1 body length per second, some of which are shown in the figure. The existing fast soft robots are generally insect scale and tethered, having little space for onboard sensing. There are several challenges for developing fast soft robots, three of which are listed and will be addressed in this research. The first challenge is in developing reliable, high-speed, and high-power density actuators for soft robots. Although many soft actuation methods have been developed, very few of which can achieve reliable, powerful, and fast actuation suitable for dynamic mobile locomotion. Stacked DEA is close to this goal, while it is hard to manufacture. As compared, geared brushless motors are rigid, fast, and widely available. In fact, many legged robots use motors as actuators. For example, the hexapod shown on the right figure can run at a speed of 4.9 meters per second or 47 body lengths per second. Thus, combining motors with soft structural material could be a good way to create fast, soft robots with good manufacturability. Due to large deformation, controlling a high-speed soft robot can be challenging. A realistic and fast soft body simulator could help in modeling and controlling the soft robots. PyBullet and Mojoku have been used extensively in research for rigid body simulation. Compared to rigid body simulation, soft body simulation is more computationally expensive due to the high degrees of freedom. Several methods are suitable for large-scale real-time soft body simulation. For example, the differentiable simulator Taichi, the unified particle simulator Flex, and the CUDA accelerated spring mass-based simulator Titan. Finally, free-form manufacturing of soft robots has been challenging. Compared to subtractive manufacturing, 3D printing enables rapid prototyping for complex objects. It also enables the design to be open-sourced and fabricated with little specialized tooling. Flexible material such as TPU are widely available and can be printed with an off-the-shelf 3D printer. With these challenges in mind, we present an open-source, untethered soft quadrupedal robot named Flexapod for researching soft dynamic locomotion. We printed the robot with a desktop 3D printer using flexible TPU material. By varying 3D printing parameters such as infill density and flow rate, a 3D printer can fabricate soft parts with varying metamaterial stiffness, which is summarized in Figure A. The Flexapod soft body was printed with 20% infill density and 90% flow, while the softer leg was printed with 16% infill density and 80% flow. The flexible material combined with gyroid infill lead to soft and flexible structure. 96 volume% of the 3D printed parts are soft, making the robot 80% soft by volume. The legs are hollow to achieve low inertia as well as good compliance, As you can see, the legs can be bent and compressed very easily. The soft legs are driven by geared servo motors to achieve high-speed locomotions with adequate torque. The electronics and batteries are enclosed by the soft body to be protected against the collision. One advantage of our soft robot is that it can resist shock and collision. To demonstrate that, we dropped the robot from 1.2 meters and 2 meters. In the video, the robot passively deforms to reduce shock and stabilize itself when hitting the ground. The electrical system enables wireless control of the soft robot using a computer. The design is modularized such that its assembly is straightforward. Based on the spring mass simulator Titan, we developed a real-time soft body simulation to simulate soft robots with revolute joints. We used the simulator to evaluate and optimize its mechanical design and gate controller. To validate the simulation, we compared locomotion speed using pace gate and bounding gate in simulation and reality. We compared the average velocity of the robot under different gates and speeds. The x-axis shows the velocity in reality, and the y-axis shows the velocity in simulation. If the simulation matches the reality perfectly, all sampled points should be on the ideal line, which is the dashed red line. Under the same simulation setting, the bounding gate shown as the orange points has small seam-to-real gap, while the pace gate shown as the blue points are good at low and high speed, but slightly diverges from the ideal line at middle speed. With the verified simulator, we developed and optimized the various gates. On grass terrain, the soft robot can run stably at greater than 2 body lengths per second using pace gate and bounding gate. Using pace gate, the soft robot can run as high as 2.5 body lengths per second on a carpet. To further demonstrate its dynamic capability enabled by the geared brushless motor, we show that the Flexopod can do backflips in different environments. Finally, we demonstrate that the Flexopod can locomote at unstructured terrain. We hope this soft robot, along with its verified simulator, can make it easier for researchers to study dynamic locomotion for soft robots. Thank you.